Okay, hi again, students. I know I told you in a previous video this will be the last one on error propagation, but let me just wrap up this here in one final video. I just had a few more thoughts on it, and I wanted to also make another link back to the cratering experiment. So sorry about that. But anyway, we're talking about error propagation, and I hope you get the general idea now. Okay, so we'll wrap it up. And the idea is that if you happen to make a direct measurement of, in this case here, say A and its uncertainty and B and its uncertainty, we're talking about how to propagate these errors here of A and B into a derived quantity, which in this case is C. So as we've seen in the case where you add two quantities together, the uncertainties just add, and that's a perfectly okay way of estimating the uncertainty under addition. If you like, you can also look at the quadrature addition, which looks like a lot like a distance formula, sum of the squares. That's okay too. And of course, if you have multiplication, like A times B, and I even went and put some powers in here just to show you the generality of the technique here, then the uncertainty in the C would, at sort of the core level, be these fractional uncertainties between delta A and B. So delta A over A and delta B over B, you see it look just like a percent error without the times 100. And of course, you square them, they're added in quadrature. And if you happen to have a power in there, then the power sort of just gets put as a coefficient in front of the fractional error. And that way you can work on multiplication and division all with the same formula. So I just wanted to point out that if you look in the front cover of your book by Taylor, the front cover sort of covers all this in kind of a nice way. And the formulas are so common that they're just in the front cover because you can just refer to them without having to dig through the book or go through the theory and so on and so forth. So it gives you a little bit of setup here, talking about the x best and the uncertainty there. And these are the things, the fractional uncertainties that we sort of see popping up in there. But then the real meat of the formulas comes as we get here. So the saying here, if Q is the sum and difference here of a bunch of terms here, then here is the uncertainty in Q, given the derived quantity. Just add the uncertainties up or add them in quadrature, either way. And he's making the point here that if you just add the uncertainties up, that's always going to be the largest possible uncertainty you could ever get. And that's a good thing to guide yourself with. Just go with the largest one. Easy to defend in court, right? Likewise, they're saying that if you have a big product like this, product maybe or in a quotient, some multiplication and division, well, it doesn't matter if it's a multiply or divide. You can either just add all the fractional uncertainties, kind of like this one up here, that will always give you the largest uncertainty to deal with, or you could do the quadrature addition right here, which is the one up there, which gives you probably a better approximation of the uncertainty, a little bit smaller. And of course, if the exponent is in there, they would be sort of inserted inside the parentheses or the way indicated above. And so they go on a bit more here. You can see there's a few others you can sort of wonder about here. If you just multiply a measured quantity by a constant, which is known exactly, in other words, uncertainty is 0. It's a fairly simple relationship here, but remembering if you know something exactly, then it'll be something like delta B over B would be the fractional uncertainty. But of course, in this case here, delta B is equal to 0, right? Because you know the term exactly, and so its fractional uncertainty won't appear in any of the formulas that we have. I wanted to also just show you where this one comes from, because it's one of my personal favorites. I just sort of love how it comes out. I'll show you where that one comes from. And of course, lastly, this is that power right here. When you have an exponent, you can just see that it looks a lot like the fractional uncertainty, but as I mentioned here, the power just sort of goes right in the front there, and then you can go ahead and add them or square them, or add them either directly or in quadrature the way we said. So let's just end this video here by talking about this one right here, that what happens if you have to run a measured quantity through a function. And the reason why I'm doing that here is because if you remember from the cratering lab here, the key function, like the f of x here that we had to run our data through, was the natural log of x. And that's what the scaling law sort of demanded we do to see how the cratering energy and diameter would scale together. So I just want to sort of show you where that uncertainty business came from. And it's just kind of fun the way it works. And let me just see if I can get a sketch going here. So basically, what you have at issue here is that you sort of have a function here between y and x, right? Usual thing here. And let's just say that x is what you measured here, and right here, this is your best version of x that you've measured right here. This is x best right here. And you want to know, sort of in your analysis here, you have to map it into function y. You want to know what would be the y best for that. And they're linked by a function. I'll just sort of sketch an arbitrary function up here. So this is sort of the f of x that we have to run x through. So if you remember in the cratering lab, all of our energy and diameter data points had to go through a natural log. That was the function there. So the way this works is pretty straightforward. I just kind of like the way it works. That if you have the x best here, that'll get mapped right up there into y best. It sort of feels like a calculus problem right there. So that's x right there. That would be y, say, best right there. Then if you go out sort of this way where you have like maybe x best plus the uncertainty sort of in the worst case, that'll throw you way over here, but of course that'll get mapped into y over this way, right? So there's sort of, this will be maybe y plus delta y, something like that. And again, our goal is to figure out what this exact mapping is going to be. And if I go back over here, I will have x best minus delta x, okay? And that, of course, gets mapped into y. You'll clear down here, something like that. My drawing isn't the best, but there you go. But this point right here would be y minus delta y, something like that. Okay, so the thing is what is this mapping going to be? And if you just sort of look at it, you can see here that on the graph, this distance right here is basically delta y, so the uncertainty in y. That's what we're trying to shoot for, right? And if you look very carefully sort of at the way it looks here, you can see that delta y is basically the function f of x plus delta x, right? X plus delta x, so you're going way over to here. This is the function evaluated at x plus delta x. And then this point right here is just you just subtract and you get f at just x, right? So you're just sort of evaluating x at this point right here. So really delta y, as I've drawn by the yellow arrow here, is just the difference between the function evaluated at x plus delta x and the function just evaluated at x, right? This vertical distance right in here. So that's sort of what I've written. And now really just to wrap it up, and I just sort of like the way this works here. I don't know why, I just kind of like it. But if I just go ahead and say divide both sides by delta x for no real reason, something like that, then if you do that, if you look at this side over here, it looks an awful lot like a derivative, doesn't it? Because you have f of x plus delta x minus f of x. Here's your f of x plus delta x minus f of x all over delta x. And what you can sort of say then, if you don't really do this in error analysis, but in the limit is delta x sort of goes to 0, right? And sort of what you're always assuming when you do your experimental work here, that your uncertainties are small. Hopefully you're working within that regime. And so what will happen over here, I'm running out of room a little bit here, but this left side, this right side over here just becomes basically df dx. And so you're in this situation here where the uncertainty in y divided by the uncertainty in x, that's just sort of this left-hand side over here, just copying, is equal to df dx, okay? So I am definitely running out of room now. Let's see if I can just pick this up and take it down here. Let me just copy this, and I'll just continue this discussion down here after I have these scanned pages in here. Okay, let me add another blank page there. There we go. Okay, so I'll just put it down here. There it is. There's my last form I ended with there. And of course, so the uncertainty in y then is just going to be df dx times the uncertainty in x. And so this is sort of our result. And this is what they have right here in our book by Taylor here in the front cover, sort of this formula right here. There it is, my favorite one. Okay, and you put the absolute value sign in there so you don't get sort of messed up with any signs of the derivative that might pop up. And so what happened in the cratering experiment? Well, in the cratering experiment, the f of x was the log of x. That's what we had to run the data through in order to get it work out. So the uncertainty in y then would just be, well, what's df dx if it's log? Well, it's 1 over x times delta x. And so the uncertainty in y then just became delta x over x. And this is what we used to transform all of the diameter data points into that log space. Okay, so this space right here, remember y, this is sort of like the log space for the scaling law. And all of this business over here, these were the measured values. So I just wanted to come full circle on the crater and say that's why, you know, when we wanted the uncertainty in the diameter of the crater in log space, that was just equal to the real uncertainty of the diameter of the crater that we actually measured divided by the diameter of the crater itself. So all of you had the MATLAB code that did that transformation. That's where it comes from. Okay, so with that then, I just want to encourage you then that whenever you need to start wondering about uncertainties, just pull these formulas from the front cover of your error analysis book by Taylor. They're all in there. You have addition, you have multiplication and division, you have an exact multiplication, you have my favorite one there when you run it through a function, you have the power law right there, and you know what? You just go and use these things as needed. You don't always have to worry about derivations and that kind of thing. Okay, that's all for this segment on error propagation.